Greetings, welcome to our video solutions for Superquiz 2. And this is the solution for problem 1 from that Superquiz, which asks us to use the well-ordering axiom to explain why any two positive integers must have a least common multiple. So let's jump right in and remind ourselves, okay, what is the least common multiple? So if I have two integers, positive integers, a and b, the least common multiple, which we denote by LCM of a and b, is the smallest positive integer. All right, of course, if we don't say positive, then of course we might jump into the negatives, and that's not what we're looking for. The smallest positive integer that is a multiple of both a and b. Okay, and the claim is that amongst all such positive integers, there is a smallest one, and we want to use the well-ordering axiom to justify that statement. So it's going to be useful, of course, to have the well-ordering axiom, and the basic one that we gave in class was what I denoted WOA greater than or equal to 0, right? Which says that every non-empty, of course, that's a key point there, every non-empty subset of the non-negative integers has a smallest element. Okay. In this particular problem, of course, we're looking at subsets now of the positive integers. So if we wanted, we could replace with greater than 0, where it's the exact same statement, right? Only we have z positive here. But it's not particularly important because if we have a subset of the positive integers, that will also be a subset of the non-negative integers. So going with the original is probably fine here. Okay, so if we want to get a smallest element, right, which is exactly what we're asked to find here when we try to show that the least common multiple exists, we should be able to use the well-ordering axiom as long as we can determine the correct non-empty subset, right? Okay, so how are we going to do that? Well, if I start with elements A and B, instead of asking for what is the smallest of all of the common multiples, what if we just ask for what are all of the common multiples, or at least all the positive common multiples? So let's let S be the set of all positive common multiples of A and B. Okay, so if we wanted to write this in set builder notation, right? So i.e. S is equal to the set of all, say, Z in Z greater than 0, so all positive integers Z, such that Z should be a multiple of A and a multiple of B. So A should divide Z and B should divide Z. All right. In order to use the well-ordering axiom, though, we need to establish that we have a non-empty set. So it's not a priori obvious that S has anything in it. Of course, just a little bit of thought will let you see that, well, there is something in there, namely A times B is an element of S, since A divides AB and B divides AB. Right? How do you know it divides? Well, it divides because A times B is equal to AB, and B divides AB because B times A is equal to AB. All right, so this implies that S is non-empty. So by the well-ordering axiom, right? Remember, of course, like we should say here, right? Every Z here is a positive integer, so this is a subset of Z greater than 0, or if you like, well, certainly not the same thing, Z greater than or equal to 0. So by well-ordering axiom, either one you like, S contains a smallest element. So amongst all common multiples, there is a smallest one, and therefore the LCM exists.